Renato is a professor in theoretical physics at ETH in Zurich, known for his work on quantum information science, quantum thermodynamics, and the foundations of quantum physics, including groundbreaking work on the security of quantum key distribution. So go ahead, please, Renato.
Okay. Is it now visible?
Yes.
Okay, perfect. I'm sorry for that. So I cannot see the questions either. So if there is an urgent question or anything, I'm also happy to answer it during my talk.
Renato, just before you start, to give you some instructions, I will be reading the questions here. Do you prefer that I ask the questions as they pop up, or do you prefer to allocate time at the end and then we go over all of them in order?
I would prefer to answer them immediately.
Okay.
Okay, so I will talk about the ultimate physical limits of privacy, and what I mean by that should become clear in a minute. I will focus in my talk on what is called secure message transmission. So that's basically the usual task, that we have some secret message and we want to send it from A to B, or here from Alice to Bob, over an insecure connection, which is here represented as a cloud. And basically, just to make the clear distinction to the previous talks, which I enjoyed very much, is that here we are talking kind of the opposite from before. So before we heard about the dangers and countermeasures that we need to take if quantum technology is used by eavesdroppers, by our adversaries or crypto analysts. And this is mostly, of course, the quantum technology of quantum computers, as we have heard in the previous talks. In this particular case, I mean, the illustration would be this little atom, which stands for the quantum technologies, in the hands of somewhere in the cloud, and it's not quite controllable. And now, what I am going to talk about is, in a sense, the irony, one could say, is that the same technology that gave rise to these problems we are now dealing with also gives us tools in our hands to solve the problem, although at a high cost, as I will explain in a minute. So I will talk about the use of quantum technology by the legitimate users. So here, this is Alice and Bob. So the atom is now in their hands. And the adversary may have a supercomputer, even a quantum computer, and so on. That is all included. But the point is, we are now using quantum technology on the user side. So specifically, I will talk about something that is usually called quantum cryptography or quantum key distribution. Quantum cryptography is maybe the broader area that includes also other tasks than secure message transmission. I will, however, as I said, focus on secure message transmission. And here the key ideas came from these three gentlemen, Charlie Bennett, Gilles Brassard, and Arthur Eckert, who developed all in the 80s and 90s protocols for quantum key distribution, which is a protocol I will explain shortly. Basically, I mean, the main thing to keep in mind, and this is also the reason, I would say the main reason why we are not using quantum cryptography today, is that it needs new infrastructure. So actually, quantum cryptography is, in a sense, much easier than building a quantum computer. We can communicate using quantum cryptography with lasers and optical devices that are available today. However, we need to be able to transport a quantum system, which is here represented as an atom, but in practice is usually a photon, a light particle. We need to communicate that from Alice to Bob. And this is possible. We can use optical fibers. However, we need to have a direct point-to-point connection between Alice and Bob. And in addition, this connection has to be quite lossless and clean. And that means that if I now wanted to talk to you with quantum cryptography, I simply cannot do that because we don't have a direct such connection. And as I will explain later, we can also not use amplifiers, at least not with current technology. So the problem is not the technology that Alice and Bob are using. The problem is really that the infrastructure, the communication channels that we need are not yet there. So what would these communication channels be? One possibility is free space communication. So the light particles, the photons, would just be sent over free space, and this could be via satellite. I will come back to that later. Or, and this is the more common implementation, we could use optical fibers. And that's, of course, a technology that is available. However, because of losses in the fibers, we would only achieve relatively short distances. And by relatively short, I mean of the order of 100 kilometers, but not longer. So, okay, I started kind of with the drawback. So these are the high costs that come with implementing quantum cryptography. Now I would like to briefly talk about the advantages once we would be ready to invest this into that technology. And that's a very high level of security, or what I called in the title, in a sense, the ultimate secrecy. And the ultimate I will come back to that at the very end of the talk. What I'm saying now is maybe not yet ultimate. So the idea is here that we have Alice and Bob. These are the two partners who would like to communicate. And what is marked in green is the part we still have to make assumptions about. So we have to assume that Alice is in a kind of isolated lab. Information doesn't just leak out. That seems to be a necessary assumption in order to do cryptography. The same for Bob. And everything in between that is marked in red is untrusted, which means we don't make any assumptions about that part. So that part could be completely controlled by an adversary. Also, the adversary could have unlimited computing power. However, there is one additional assumption that is sometimes not mentioned very explicitly, which is we need to assume that Alice and Bob can communicate over a classical authentic channel. This is going to be necessary. However, this is not such a big deal because in principle we can achieve authenticity by even in an information theoretic manner, by starting from a short shared secret, like a short password or so. For the rest of the talk, I will just assume that Alice and Bob have that channel available. And what I mean by an authentic channel is basically just a classic, like something like a classical telephone line, where it would be very hard to imitate my voice. Maybe that's no longer true with artificial intelligence, but that's just as an illustration. But there is no privacy there, so everyone could listen to that channel potentially. And then we assume that in addition, we have this quantum communication channel, which could be, as I said, an optical fiber or a free space link or a satellite link, and nothing is assumed about that channel. So this could be arbitrarily controlled by an adversary. Now, the adversary, in addition, may have arbitrary computing power, and that's the symbol you see below. Like this is a huge computer, and what we would like to achieve is that we would like to transmit the message from Alice and Bob in such a way that Eve cannot retrieve any information about the message, even if she had infinite time or computing resources available to her. Now, the way, if I would now not make a condition, this would be a bit questionable, because what an adversary can do, from what I said, is, and because we don't assume anything about the quantum channel, the adversary could just cut the channel into two pieces and no communication would be possible. So the more precise statement is the following. Alice can send a message, try to send a message to Bob. Now what can happen is that Eve just messes up this communication and the message will not arrive. However, if the message arrives, so in any case, independently of whether the message arrives at Bob's place, Eve can never read the message. So the only thing that Eve could potentially do is to basically jam the channel and make it impossible for the two to communicate. But whatever she does will never provide her with information about the message Alice wanted to send to Bob. So that's the guarantee. So we have, in that sense, an absolute security guarantee. We have no absolute guarantee that the message actually arrives, but that's clearly not possible because Eve cannot, under this channel model, because Eve can always destroy the channel. Now, one of the basic ideas behind quantum cryptography is that one basically subdivides the task of secure message transmission into two parts, and only one of them is a quantum protocol, actually. That's what I call here phase one. That's quantum key distribution. So the abbreviation QKD, that I will use in the following stands for that. And the second phase is a purely classical phase. So you use the key that is generated by this quantum phase in order to encrypt messages in a perfectly secure way. And this is by one-time pad encryption. And I assume that many in the audience know what that is. I will nonetheless very briefly explain what it is, just to remind people that it's actually perfectly secure. So I start in that sense with phase 2, which is, as I said, something completely classical, and it uses only a classical channel. So in the following, I will always use these yellow lines for classical channels and orange ones for quantum ones, for quantum channels where I need this photon to transmit the photon or something like that. So one-time pad encryption is something very simple. We have a key, for example, a bit and a message. Let's assume it's also a bit. And the encryption just works by adding the key and the message modulo 2. And then the decryption is again addition modulo 2, which is actually equivalent to the subtraction. And you can see that this is certainly correct in the sense that if I add the same key to the message that I subtract later again in the decryption, I will get the message back. Why is it secure? It's secure because if you imagine that you see the ciphertext, like you see, for example, that it has a particular value, then this obviously doesn't tell you anything now about the message, because the message could now either have been 0, I mean, here you saw a 1, but the message could be a 0 and the key a 1, or the opposite. And if you only, so this proves that if you only see the ciphertext, that doesn't give you any information you didn't already have potentially about the message. So it doesn't provide you any extra information. So, which means wiretapping that communication is useless. However, and this is the big problem, and also the, let's say, reason for the name, why one-time pad. The one-time pad should only be used once per bit. So each message bit should only be encrypted with 1 key bit. And you see the problem here, if you see a ciphertext, and you know the same key bit has been used to encrypt 2 different message bits, then you still don't know the message bit, but you know they are equal in this particular case. And so, for example, you know they are either both 0 or both 1. So this is why we really need 1 fresh key bit to encrypt every new message bit. So we would need an enormously long key, which would make this encryption scheme completely impractical, because we would first need to communicate a key as long as the message before starting to do encryption. Now, what quantum key distribution does is precisely to provide that key, or a constant stream of keys, so that we can keep encrypting using one-time pad encryption while getting fresh, or in the correct way, meaning that we use 1 fresh key bit for each message bit. So in other words, what this diagram shows is how these 2 phases play together. We have now seen phase 2. We need the QKD scheme needs to provide 1 key bit per message bit. So the speed of the QKD protocol will also determine at the end how fast we can communicate. So basically, the amount of key produced per second corresponds to the amount of bits we can at the end communicate per message. Yes.
We have a question here from the audience by Hassan Sayed.
Yes.
What are some, if any, developments for quantum communication channel in the cloud space, AWS, Google, etc.? I know that AWS has private link allowing connection between VPCs without exposure to the public internet.
Mm-hmm. Yeah, I mean, what I'm actually explaining here, so these 2 phases, this is if we really want to achieve perfect security. Now, in practice, what is done is that people use that key, that orange key that is shown here, just as a seed for an AES, for example. So the one-time pad encryption is replaced by an AES scheme, for example. Then you can, of course, communicate much faster because you don't need 1 key bit per message bit. However, then you are basically back with some level of some computational security. So in practice, this may still be good enough for many purposes, but it's very hard to make a clean security statement about that. So while this is kind of useful to do, I will here just explain in a sense the ultimate thing we would like to do once we have very fast QKD schemes. And in that case, we would not combine it with any computationally secure scheme, because we are really interested in making this, let's say, ultimate statement that the cryptography is secure even if an adversary had infinite computing power, which would not be the case if we replaced here the OTP by AES, because by collecting sufficient ciphertext, the adversary could still decrypt the message, and after sufficient time. I hope that answers that question. So let me therefore come to phase 1. And phase 1 is the actual quantum part of the whole story. So here there are 2 different schemes that have been proposed. I showed the 3 gentlemen before. Gilles Brassard and Charlie Bennett proposed a different scheme from the one I will now explain. I will explain the one by Eckert, which is a little bit less practical nowadays, but it has, in a sense, a higher security guarantee, as I will explain later on. So here the idea is the following. Alice, here on the left, will generate 2 quantum particles which are entangled. And I will in a moment explain what that means. For the moment, just think of entanglement as some type of correlation between 2 quantum particles. And then she sends 1 particle of this pair over to Bob. And the correlation is something that is not bound to distance, will remain. So this so-called entanglement will still be there. Now, what is entanglement? Let me explain that before proceeding. And instead of explaining it now for an arbitrary atom, let's go to the simple case of a single qubit. So a qubit is, we have heard about qubits in the first talk. They're kind of the smallest unit of information if we talk about quantum information. And so that's why I chose them. And I choose here in this picture a qubit as a spin. So this is some object that can point in an arbitrary spatial direction. And I could encode information into that. For example, saying that if it points upwards, it's a 0 and downwards a 1. But because it's a qubit, it also has other directions. It could, for example, point to the right, and I could call that 0 bar, or to the left, and I could call that 1 bar. So that's something you have heard about in the first talk. And in quantum computing, we, of course, act on these qubits and also correlate them and entangle them with gates. Here, we just produce entanglement between 2 of them. So technically, we would say they are now in a superposition state between both being 0 and both being 1. But what does that mean? So what it means, or what is the relevant property, is the following. So first of all, you see that arrows have disappeared. So if I generate a correlated qubit, it doesn't have a fixed direction, neither of them. However, I can now measure each of the qubits. So let's say the one on the left is Alice's qubit and the one on the right Bob's qubit. And I could choose to check whether it points up or down. And that's now something one has to know about quantum physics. I cannot just ask, what is your direction? I can only fix 2 directions, for example, up versus down, and ask which of the 2 is it. And that's what we call a measurement. And here 0, 1 would mean, in the encoding I've shown before, distinguish up from down. And now what happens if these qubits are entangled is I will get an answer, for example, 1, and immediately, I mean, the language is always a bit dangerous, but what certainly happens is that the other qubit will now also point down. So depending on the result I get, I will have a behavior. I can describe the behavior of the one on Bob's side, on the right-hand side, and say this also points down. So this is what entanglement. So entanglement has this property, and the same now holds if I would decide to measure left versus right. I can always measure 2 opposite directions or distinguish them, and whenever I do that, it will have one of them. So it will never say, oh, I'm actually up. It will always decide for one of them. And so if it decides I'm actually pointing to the left, then the other qubit will also point to the left. Now, why is this property so useful? So I will just mention these things without proof. One could, in principle, now, from what I said, already go to prove these things. But one of them is what is called certifiability. So let's suppose that an adversary would try to modify this correlation. For example, I mean, as I explained before, in the protocol, one of these qubits or both qubits will be prepared on one side by Alice, and then one will be sent over a quantum channel to Bob. But Eve may sit on this channel and somehow try to change the state of that qubit that is traveling to Bob. And if she manipulates that qubit going to Bob, then this behavior that I've just shown before will no longer hold. So in particular, in this example, you see Alice now would measure in this left versus right, so the 0 bar versus 1 bar, and get an outcome 1 bar. But now on Bob's side, something arbitrary may happen. For example, a 0 may come out. So the behavior would be changed as soon as the adversary would somehow interfere with this. Now, if the adversary doesn't interfere, and that's the second property, so this property I call certifiability. Alice and Bob can basically check whether it's correctly entangled. And if it's correctly entangled, then comes the second important property, the monogamy property, which says that if they are entangled in the way I described, these two qubits cannot be correlated with anything else. So formally, it means it's a product state. This is this red part here, so it's not correlated to the rest. But you can think of this just as if the two qubits are correlated in that way, any correlation with anything else is by the laws of physics ruled out. So there's no way they can be correlated with anything else. So this is, in combination, these two properties are extremely powerful because first of all, you can check whether you have this correlation, that's the certifiability. And second, once you know that they are in this correlated or entangled state, you know they are not correlated with anything else. And now, of course, if Alice and Bob would measure the two qubits, they get a key, which is the 0 or 1 that we have seen before, that comes out of these measurements. And because the qubits are not correlated with anything else, the key will also not be correlated with anything else. So that's basically the idea. So we create entanglement, or Alice and Bob create entanglement and measure. And by the properties, by the monogamy property of entanglement, after they certified that it's correctly entangled, they know their key will be uncorrelated to the adversary. Of course, in practice, there may be noise and it's more complicated, but that's basically the idea. So a QKD protocol now consists of the following. Alice and Bob use the communication channel. So that's basically a summary of what I said. They use the communication channel, this orange channel, to distribute entanglement. So Alice locally prepares the pair and sends one of them to Bob. Then they do statistical checks. They just sacrifice a few of these pairs of qubits to check whether an adversary was on the channel. If this is not the case, and I mean, to check that, they need to communicate over the authentic channel, by the way, that's why it's used. But if they find that they are correctly entangled, they can carry out measurements to get a key. And these keys will be perfectly correlated and complete among themselves, but completely uncorrelated to the adversary. And that's precisely what we want from a perfect key. So now they can use the key for the second phase, which was the one-time pad encryption. So in summary, we have these two phases. In the first, we create entanglement. From that, generate the key. And in the second, we use one-time pad encryption to encrypt messages. Okay, so that concludes my description of how quantum cryptography works. And now one could ask, what's now the status? Do we have these things? Can we build them? And the answer is yes, there are already companies that sell devices. And actually, the protocols that are implemented in the commercially available devices is a little bit different. It's a so-called prepare and measure scheme, where you could think of it as Alice already measures her qubit before she even sends anything off to Bob. So she doesn't have to store anything, any quantum coherence, and that still works as can be shown. And that's the so-called BB84 or Bennett-Brassard 84 protocol. So it's a bit different, but it has the same security guaranteed, and the security proof goes via the same arguments that I've shown here, which can of course be made mathematically rigorous. But this is still difficult. So the main problem, as I pointed out at the beginning, is we need these direct connections, and that's very technologically very challenging thing to do. And here I have to say that the Chinese are ahead. So they have already built a quantum secured network. So this consists of links that are fiber optical and combined with satellite links. So they actually managed already to distribute entanglement from a satellite, and they can use that to generate keys. Basically, in the way I explained, there were some simplifications that had to be made in practice, but they have the technology to implement what I just said before, even for on free space communication from satellites to Earth. Now one could ask, does this actually really work in practice? So as I said, it works, but works in cryptography is always dangerous work, because work could mean I can indeed send a message from Alice to Bob, but the question, was it really secure in practice? And the answer, unfortunately, is currently often no. And the reason is the following. So currently the whole technology that we are using to encrypt or to do what I just said, so we have to generate entanglement, we have to send entangled states from Alice and Bob and so on. All this technology is still in its childhood, in a very early stage, and the hardware that we have often doesn't do what it's supposed to do. So actually, if you look at now this encryption, if you look at the QKD scheme, so it deals with some photons, and if you actually look into a lab, it looks like a very complicated arrangement of lasers and stuff. So that's actually a part of an experiment in which we were also involved as theorists. I don't understand the experimental part, but it's certainly very complicated and even hard to verify whether it does the right thing. And so the problem is that it actually often, just because of imperfections of the hardware, doesn't do the right thing. And so if for example, instead of sending one particle, it accidentally sends two, that's, for example, a problem. And that's a real problem and has been exploited by quantum hackers. So you see here one of the world's most famous quantum hackers, Vadim Makarov, with his suitcase, with which he travels around the world and hacks quantum crypto systems. And I have to stress, he doesn't hack the principle, but he exploits the fact that the technological implementation is not proper. And so the question is, how can we deal with that? One is to wait until we have better hardware. I think classical cryptography in the past suffered, or maybe still now partially, suffers from a similar problem. A hardware implementation may leak information to the outside via side channels, and we have that problem also exists in quantum. I should say it's not worse in principle, it's just worse because we have less experience, because it's a new technology. But here, and that's an interesting last thing I would like to say, is there is also a very fundamental way to prevent that, and that's called device-independent cryptography. And before I had this trust graph of red means that's controlled by Eve, and now what you see is that Eve is here allowed to even control a part of the device. So the encryption device that you see in this white box is partially in the red zone, which means we make the assumption, or we no longer assume that the encryption mechanism is completely under control of Alice. And that's really kind of a way to take into account that the devices we are using today are not fully trusted or imperfect. Now it turns out that even with this increase or reduced trust assumption, it's still possible to generate secure keys, which is quite remarkable. So we don't even need to trust Alice and Bob's devices and can still generate the key. However, it's even more demanding on the technology. And this has recently been done. Here you see a lab of ETH Zurich of Professor Andreas Wallraff, who actually generates entanglement and can do so-called device-independent cryptography. And that's just a device that in principle allows that. And here, I think, in contrast to what I said about satellites, Europe is actually ahead. There was recently an experiment by a group in Oxford where device-independent cryptography could be demonstrated in practice, but this is still in the lab stage, so the distance was extremely short, just a few meters, but in principle, the technology works. Okay, so this brings me already to the end. So I think the point is that we have a new technology, quantum technology, and it comes with challenges, in particular the fact that our public key crypto systems like RSA and Diffie-Hellman will be broken by quantum computers. We don't know when, but that's at least something we have to take into account, the possibility we have to take into account. But on the other hand, the technology also allows us to basically for a long-term solution. And by long-term, I mean here the security will no longer depend on any development in computing, because it's based on the laws of quantum theory, on these properties of entanglement that I mentioned before, and on no other computational assumption. So once we have the infrastructure, which, as I said, is at the moment not the case and probably too expensive, but in the far future, once we have that, we will have a cryptographic technique that allows us to have, in a sense, really long-term, or one could even say everlasting security. Okay, that's also, I just wanted to thank the members of my group, as you see here on the picture. And I also, for those who want to know more about how this device-independent cryptography actually works, I refer to this an article in this journal that I wrote together with Arthur Eckert. And if you cannot access it because of maybe it costs, then please send me a message and I can send you a version.
Renato, thank you so much. And that was a fascinating talk. We have a question here. We have a question here by Maria. A generic question: what are the financial related applications that you see for quantum key distribution? Like she probably means applications by banks or industries in the financial domain.
Yes, so I don't necessarily see why it's more relevant for finance than any other let's say use case where we need secure communication, like even in military applications. However, indeed, the first actual users of the commercial devices were banks. So one of the first companies that is still existing and actually also very productive in Switzerland has sold one of their first commercial devices to banks, who then connected one of their data centers, which were, I guess, somewhere in the Swiss mountains, deep under the rocks, with their headquarters, and they have secured that with a quantum cryptography link. I should say that, I mean, to be honest, that was probably more a marketing thing, because the data rate was probably quite low. But I think this is a typical application, because here one could say that the special infrastructure to have an optical fiber from this data storage place to the headquarters is maybe something one can afford for that. So I think it's an example case. But there are certainly, I mean, I don't see anything that makes it particularly useful for finance, or I think it's more like high security. So there currently, at least, there are applications where we have really a very high requirement on the security, and on the other hand, a very large budget to invest in the required infrastructure.
Renato, I have two quick questions of myself here.
Yes.
One more philosophical, okay, the other one more practical. So the philosophical one is, I mean, you work on the very foundations of quantum mechanics, and have done important contributions there. So I would like to ask you, what are your views on what can quantum information, quantum cryptography contribute to physics and the foundations of physics itself? What has happened and what are your views for the future?
Okay, I really like the question, because actually part of our research program is precisely to do that. So we do quantum cryptography not just for the, let's say, applications purpose, but it turns out that the way of thinking in quantum cryptography actually leads to insights in physics. And just to give an example, if you want to prove security of quantum cryptography in using the laws of quantum physics, you have to ask at some point the question, is quantum theory actually complete? Because what could happen is that there could be a proof that when we take everything we know into account that we know from quantum physics and show the adversary has no information about the key, how can we rule out that in a future theory that is maybe better than quantum theory and maybe allows us to make better prediction, that this future theory has additional elements that would actually be correlated to the key? And it turns out this cannot be the case. So what came out of this cryptographic research was kind of a very strong completeness statement saying that it's impossible to add any information to quantum theory that makes it more predictable for the setups you already know. So it doesn't mean that we cannot have new forces or anything, but it means that if we take a cryptographic setup and prove within quantum theory that it's secure, then it's also secure beyond quantum theory. So quantum theory is in that sense complete. And nowadays, this research goes even further. So there are even now considerations in quantum gravity that rely on concepts in cryptography. So there were particular entropy measures introduced in cryptography, smooth entropies. Anders, and you probably know well about them, but these really came from cryptography, from analyzing privacy amplification, and they are now used to study the behavior of Hawking radiation of black holes. And it turns out that these are just the right entropy measures to do that compared to the usual von Neumann entropy. So there's really a very interesting mutual influence between foundations research and cryptography.
That's just fascinating. We are over time, but maybe you can very quickly answer two questions here. The first question, if I understand it well, is asking about some standardization
Yes.
for effort.
Yes.
Or specification is the word being used, but I'm guessing standardization effort in this arena. And the second one is, can you combine post-quantum cryptography and QKD?
Yes. Okay, these are two excellent questions. So let me try to answer them short. So there are efforts to standardize QKD. They are already started very early on. One of the proponents here is Norbert Lütkenhaus, one of my colleagues at the University of Waterloo, and he's really driving that effort. So we are also collaborating with offices in Germany that work towards that goal. I think it's a long-term goal, but there's work in progress. It's maybe a bit early still because it's, as I said, a lot of this technology is still in early stages. Now, so the question about combining this with other schemes, I think this is certainly something I would do if, so let's suppose I had now a QKD scheme available because of what I just said, these problems that the technology is still at the early stage. It could easily happen that there are side channels that we just by lack of experience have not detected. And such side channels can equally well exist in classical cryptography, but there people have just much more experience. And so if I combine quantum cryptography with a classical cryptographic scheme, then I kind of get advantages of the two worlds. Of course, I also get the costs of the two worlds, and this is particularly high in the quantum cryptography case. But I would certainly combine today, because of the early stage of the technology, a QKD scheme with a classical post-quantum cryptographic scheme. And then, of course, if someone doesn't decrypt immediately, because these side channels have to be used immediately, I really get still the kind of everlasting security in that sense. So I think it's very profitable to combine, and I would recommend to do that rather than using only QKD at the moment.
Thank you very much, Renato.